Armstrong and Tomek, Livy, and Thomas for putting together this very nice workshop, despite starting 5 a.m. my time, but I really enjoyed it so far. So I will talk about some ongoing work. So it's actually very much ongoing. So that's it's kind of just a beginning of trying to construct some non-planar positive geometries in a very specific case using BCFW recursion relations. So kind of a physics input to build some positive geometries which might eventually be relevant for constructing some non-planar amplitudes. So the kind of bigger goal here is to find some geometric picture for non-planar amplitudes. So we just heard from Julia, we'll hear from Nima, their interesting work working in phi cube theory. I will be here sticking with n=4 super Young mills with some potential to extend it to n=8. And in the planar case, we will basically follow some path which happens in the planar case. That's when we start with the BCFW recursion relations for tree-level amplitudes. We can interpret them as the D-log forms on some cells in positive Grassmannian, and they are related to on-shell diagrams or Flavig graphs in combinatorics. And then there is some extra structure when these things are related to triangulations of the amplituhedron. And in this talk, we will kind of try to mimic this procedure. We will start with some physics input, which will be non-adjacent shifts and BCFW recursion relations. And we will interpret them as the D-log forms on some non-planar positive geometry working here in G3N. And they will be also related to now non-planar on-shell diagrams or non-planar Flavig graphs. Okay, so let me just quickly review some physics basics here. So we will talk about tree-level amplitudes. We will do a color ordering. So we will work with the amplitudes with some given ordering 1 to n, and the amplitudes will be labeled by the labels n and k as usual, corresponding to number of particles and this SU4R charge of the helicity number k. And we will think about them as functions of lambda lambda tilde. Now, the BCFW recursion relations is a statement that we can calculate these amplitudes using factorization channels. So diagrammatically, we sum over all the factorization channels when there are products of left and right amplitudes with shifted kinematics. What is usually done is so-called adjacent shift, when we shift two adjacent particles in this ordering, let's say n and 1. And this first minimizes the number of terms which contribute in this sum. And second, the individual terms have this very nice interpretation. They preserve the planarity, they preserve this ordering, and many nice things happen then. So indeed, each BCFW term has then a dual interpretation. We can think, we can associate it that a cell in the positive Grassmannian, G plus Kn, of dimensionality 2n-4. And we construct a C matrix, which with all positive, non-negative minors. And the BCFW diagram then can be calculated using some canonical form when the parameters of the Grassmannian then are related to the external kinematics lambda and lambda tilde geometrically given by these delta functions. C dot lambda tilde is 0 and C perp dot lambda is 0. It can equivalently, we can also associate an on-shell diagram or Flavig graph planar with the BCFW term. And we can directly label the variables in this diagram. For example, phase variables or edge variables. And then the same expression is then recovered as the D-log form on these variables, again with the same kinematical, the same conditions on the C matrix, which relates the parameters of C with lambda and lambda tilde. So this is all very well understood, but it is just for the planar case with the connection with the BCFW terms. Of course, we can also draw non-planar on-shell diagrams, and it has been done in the past, and calculate these canonical forms as well. Our main goal here would be to understand the positive geometry behind it. So in this planar case, the simplest case is k equals 2 MHV amplitudes, when at each order in n there is only single BCFW term corresponding to a single on-shell diagram, and on the other side it corresponds to a top cell of G+2n. Of course, there is only one. And the positive geometry, or what we here call the positive geometry, which we will refer later, is thinking about the C matrix, the columns in the C matrix as points, in this case in P1. And these points in P1 here are just canonically ordered 1 to n on that line. And we can associate just the standard D-log form with this configuration. And so here, if we label the positions of these points like that, would be just this D-log form. And when we take the residue x1 equals x2, it corresponds to pinching these points. Now, instead of these positions, we use the lambdas. Actually, the condition c dot lambda tilde solves C being the same as the lambda matrix. And and the D-log form has this famous Park-Taylor structure, when again sending the angle bracket 1, 2 to 0, which is just the 2 by 2 determinant of these lambda spinors, corresponds to merging points 1, 2. But we can also go to the configuration. This will be some codimension 2 boundary imposing 2 constraints, when we also remove the label. So if we send 1, 2 to 0 and 2, 2, 3 to 0, there are 2 solutions. One of them removes 2 completely. In the physics language, it just sends lambda. Okay, so this is for MHV. The geometry here is just configuration of endpoints on a line. Okay, in the first really non-trivial case is an MHV at 6 points, so n equals 6, k equals 3. We use these BCFW recursion relations. We get a sum of 3 terms corresponding to 3 on-shell diagrams. Now, these are 8-dimensional cells in G+3, 6, so they are not top cells anymore. They are codimension 1, imposing 1 constraint. And the G+3, the G+3 is a geometry of 6 points in P2. We can again think about the C matrix using the column and draw this projective picture. The top cell is 9-dimensional and corresponds to the convex configuration. So this is, of course, all known for a very long time. And all the 3x3 minors here are positive, corresponding to some canonical ordering in IJK triangles, which have all the same orientation. Now the 8-dimensional cells, which we'll be interested in, have 1 constraint imposed. And here, the only thing that you can do is to impose that 3 of the points are on a line in P2. So here 1, 2, 3, the minor 1, 2, 3 is 0, would correspond to this configuration of 6 points when 1, 2, 3 is on a line. And then we can, of course, go lower in the stratification of the positive Grassmannian when we impose more and more conditions and degenerate the configuration more. Now back to the BCFW and the 6-point MHV amplitudes. So we can then associate with each BCFW term a particular configuration in G+3, 6, when 3 points are on a line, and these configurations here are these 3, either 5, 6, 1 is on a line, 1, 2, 3 is on a line, and 3, 4, 5 is on a line. And then we can solve for, so this is the configuration. We have to then solve for kinematics using these 2 conditions. on C and C perp, and it solves for the symmetric in terms of lambda lambda tilde, and then we can recover the form. So using the original prescription, the GLK invariant prescription for the old paper by Nima Arkani, Hamed, Frederick Gachazo, Jared Kaplan, and Cliff Cheng, we write this form with cyclic minors. Here, the minor 1, 2, 3 is equal to 0, so it's taken as a constraint here, and then we solve, as I said, for the kinematics, and that would be the kinematical expression that we would associate with this diagram, and that is equal to BCFW term. There is some measure d mu, which I don't specify here, but in the supersymmetric theory, it would correspond to the numerator, which has the dependence on the fermionic variables. Okay, now you see that in this expression, from the physics point of view, there are these two poles which are spurious, and they actually correspond to some spurious singular configurations in P2 when when we have 1, 2, 3 on a line and 3, 4, 5 on a line, and this is not valid. This is not a valid singularity configuration for the amplitude, despite, of course, for this individual cell is perfectly fine. But then we do the sum of over 3 terms. This is the configuration which exactly cancels between them, or the corresponding pole cancels in the form. Okay, so now let me finish the review by saying what is the general case for G3n. So we have n points in P2. The BCFW generates, if you do a particular adjacent shift, generates configurations of this form when you have points on 3 lines. The point 1 here is special, and then you distribute all other points in this way. And this is again 2n minus 4-dimensional configuration. That's the one which is relevant for physics. And once then you can write again the canonical D-log form on this configuration, attach these delta function which solves for the kinematical variables lambda lambda tilde, and what this configuration corresponds to is the famous R invariant found by these people even before all the connections to positive Grassmannia were known. And in the kinematical variables in lambda lambda tilde, it has this general form. I will talk more about the kinematics a little later, so let me not here dive in of the meaning of the denominators. Yeah, but this is all known kinematical expressions, and they are directly associated with these positive geometries, with just these 2n minus 4-dimensional cells in G plus 3n. And the BCFW recursion relations is a way how to generate them in the planar case, and it gives some particular set. Okay, now we can also, so this is the sum for the amplitude when you are summing over all the I and j. The points are ordered. Now, one comment that we will be doing here everything in the lambda lambda tilde space, but of course these R invariants can be also written in momentum Pfister space using these planar variables, and then they manifest the dual conformal symmetry, or the super dual conformal symmetry, a dual super conformal symmetry of planar n equals 4 supertriangles. So they are important objects. Okay, just a quick trivial comment that the D-log form here is more than just single poles, which you might think from the Park-Taylor factor, because once you start to take residues of this form, then you always generate just D-log factors. So you will always generate a logarithmic pole. You never hit the double pole. Here in the planar setup, it will be the structure of the poles will guarantee it. There will be no numerators, but it's starting in the non-planar setup, we will have some numerators which would have to ensure that there are only D-log. There are only D-log poles. You will never generate a double pole. Okay. Now let me let me do kind of a little bit kinematical, quick way how to get the forms in lambda lambda tilde. It's actually equivalent to what has been done in the past or what is the standard way, but it will be just very useful repackaging of that information for our case. So, and it's really using the BCFW setup and the BCFW variables now incorporated in this G3N geometry. So if we have some BCFW diagram, which looks like that, which the BCFW term, which contributes to the amplitude. Here, there are 4 points on the left, 4 points on the right, and there are these two guys which have shifted kinematics, and there is an internal line, line P, which is also on shell. Now, lambda 1 is not shifted, so lambda 1 hat is just lambda 1, but lambda 6 is shifted. And once you solve for the shift, the standard procedure such that this guy is on shell and both of the 4-point amplitudes on the sides are also on shell, you get a solution in terms of lambda lambda tilde for lambda 6, and you get a solution for lambda p. And it has this particular form, some linear combination of these lambdas. And we can just identify it. Now we will think now about this G36 configuration as a configuration of 3 lines. And moving with points on this line would mean moving with lambdas. So for example, merging points 1 and 2 just corresponds to sending the angle bracket 1, 2, 2, 0, and so on. But we will now, so it's obvious in this configuration that once you start to deform it on boundaries, you have to start also move points to these 2 special points, which I call 6 hat and p, because their lambdas directly corresponds to these lambdas in the BCFW term. Okay, so sending 3 to the line 4, 5 and going to codimension 2 boundary when the minor 3, 4, 5 is 0 corresponds to sending the angle bracket 3p to 0. Okay, so in this way we can just directly write the form for this configuration using only the angle brackets. So basically encoding that you are merging the points along this triangle. Yeah, so you can merge 1, 2, 2, 3, 3p, 4p. You cannot merge 4, 5 because 4, 5 are on a line, and you need at least 3 points on a line to be able to merge them. But you can merge 5 and 6 hat, you can merge 6 and 6 hat, and you cannot merge 6 and 1. Yeah. So these are all the allowed poles that you get. And indeed, if you now plug for lambda 6 hat and lambda p, you recover the expression that we had before from solving c dot lambda and c dot lambda tilde. So it's equivalent to it, but it's a little bit faster way how to arrive at the expression, and it's kind of nice that these points make kind of this geometric appearance here in this configuration.
Sorry, Yara, the deformed guy also enter into the numerator, or?
So here there is no numerator. Yeah, so there is no numerator here. Everything here is just in the measure. Yeah, there are some overall factors like something to the 4, which is absorbed by the some helicity factor absorbed by the numerator. But there are no numerators which kind of actively cancel some singularities here. Yeah. So
you're only listing the poles. I mean, you're not plugging in some D-log of this shifted kinematic.
Yeah. So I'm just saying that this is the full form. The numerator here, I'm hiding something in the d mu, but the numerator here is really just the helicity numerator. Yeah, there is no kind of helicity independent numerator. Yeah, yeah. Here the numerator is really just something to the 4. Yeah, some fermionic thing. While in the non-planar case, we will actually have some real numerator, which is kind of helicity independent, and which purpose would be to cancel some potential double poles. Yeah, while it's not here. Here, everything is done like in Park-Taylor factor. There is also the numerator, but this is like Park-Taylor factor, really. Yeah. Everything is just fixed by the denominator.
Yeah,
and it's also.
I just mean, okay, yeah.
Yeah. Okay, so now, and the same story is just for the general n. when the term which is relevant in BCFW has this configuration of points in G3n, and we can again identify these two intersection points, Q1 and Q2. We can kinematically identify them as their lambdas, as certain spinors. And then the D-log form that we would write on this configuration is again just the product of all these adjacent angle brackets. And then some of them will have this Q1 and Q2. So all the non-trivial poles in the R invariants really come from this Q1 and Q2 brackets. Yeah, and there are exactly 5 of them, which is exactly the fact that there are exactly 5 poles in momentum twistor space where you will not see these this angle bracket of external data. Yeah, they will come in the, they will factor out in the Park-Taylor prefactor. Okay, so here just for the notation, we will have a lot these kind of mixed brackets, and this long mixed bracket 1, 2, 3, 4, 5, 6 is just equal to that, and it's equal to sum of these angle and square brackets, just for reference.
Yeah, a quick question and comment. So first of all, here you're talking about these pictures in sort of G3n, right?
G3n, yes.
But they happen to also be pictures in twistor space, ordinary twistor space in this case, right?
Yeah.
Because if we now just go back to ordinary twistor space, we know we get support on these lines in this way.
Yeah, indeed.
So my question is then, I presume that also when these points are literally ordered in this way on the lines, in twistor space is what corresponds to a sort of positive configuration in G3n. Is that right?
Yeah, so I don't know. I think about these configurations in G3n. So that's how you also did it in these old papers. So
right.
I
think it's probably easy that it's the same.
I think it is the same. I agree, but I never go to the twistor space. But I agree. It's a good question. I think it is the same. But here I really think about just the G3n and.
I mean, eventually at high enough K, it's less useful to go to twistor space, but at least for
exactly,
it's literally the same. So it's a bunch of lines and okay.
Yeah, here is a bunch of lines. Okay, is there? So there is a question. Sorry, there is a question in the chat about merging the points. Yeah, so if you merge these points, you can directly go to these lower dimensional cells. Yeah, so if you have this configuration, for example, so the 8-dimensional cell corresponds to having 1, 2, 3 on a line. And now once you go to 7-dimensional, you can choose, do you put more things on different lines, or here, once you have 3 points on a line, you can start to merging points and then eventually removing them. So this is just going down in the stratification of G+3n. Okay, so more questions about just this planar setup before.
So there is a nice positive parameterization for these using.
Yes.
Right.
Yeah, but I'm right. Yeah, so there is a nice positive parameterization, but I'm actually kind of not doing it here. I could, but I'm not doing it here because my goal here is once I have the geometry like this one, or sorry. Any of these positive geometries in G3n, any of these cells, I just want to directly go to the form. Yeah, and this is kind of a quick way how to go to the form, because I can think about this geometry in the kinematical space as being 3 lines, and I know that all the poles would correspond to merging some points. So I basically write Park-Taylor factor for 3 lines. Yeah, modulo cases when you cannot merge, like for example, in this case, you cannot really merge 4 and 5 because there are only 2 points on the line. But again, this really just corresponds. This is a different way how to say that I'm solving these C dot lambda and C dot lambda tilde equations.
No, it's a very nice configuration space. Yeah.
So this is a fast track how to solve these equations. But yeah, in general, you would have to you can draw the on-shell diagram or play the graph for that. You can find a positive parametrization. and then you solve these equations. You solve
So I guess
the parameters in terms of lambda, lambda tilde, and plug into the DO form. That would be kind of an official way how to do it. I'm just saying you can do it like that as well.
So I guess there would be at least, I can think of at least 2 natural ways to do this in higher dimensions. Have you?
So in higher dimensions for higher, I look at
higher
G4n.
K, yeah, higher K.
Higher K. I look at G4n. Then it kind of corresponds. There are not 3 lines, there are 5 lines, but it works exactly the same. Yeah, there are the 5 lines. Yeah, the configurations of lines. I think that the general. Okay, so that's my conjecture. There is always kind of odd number of lines where the points are. These guys which are relevant for the BCFW. So it's 1 line for G2n, 3 lines for G3n, 5 lines for G5n. These 5 lines are on 2 planes. 2 different planes. It now
okay, it's not like the edges of a tetrahedron or something.
No, it's not. No, it's not. It lives only on 2 planes in.
Oh yeah, you need a cyclic orders. Okay.
Yeah, it's cyclically ordered. So all the points along these 5 lines are cyclically ordered. Yeah, and it's kind of convex. Yeah, I don't know how to think of convexity, but it looks convex. Yeah, these configurations.
The fact that they're supported on that many lines is, I think, clear again from BCFW and twistor space. But anyway,
I think so. I think so. Yeah, I think so. It is clear from that. Yeah, it's just
Sorry,
that.
Nima, for twistor space, shouldn't there be k-1 lines? Like for next symmetry, shouldn't there be only 2 lines rather than 3? And I mean the degree, like k-1, right?
Yeah,
it's 2 k. No, it's 2k plus 1 for BCFW terms.
2k plus 1. Yeah, 2k
plus
1.
They're quite high loop order.
Yeah.
Right.
I mean,
it's exactly that. Yeah, 2k plus 1. Perfect. Yeah. So that's exactly
it's genus K. Genus K ends KM, which should be.
Right. Yeah. Perfect. Yeah. So I know.
Okay. Great.
I just remember this 1-1-1-3-5 pattern for sure. So
yeah. So yeah, it's just that if you have like more general at n square MHV, if you have like more general cells of the positive Grassmannian, and they will be
talking about. Yeah, you're always talking about not generic cells of the
not general BCFW like.
But the BCFW ones, which are lower and lower dimensional in
right,
general.
they will start to be lower and lower dimensional.
Telling us in a moment might be more general for any cells, but in any case, you're restricting your attention to the cells we get from BCFW.
Exactly, because well, of course, in planar case we know everything from both sides, but the ones that I would like to generate in the non-planar case come from BCFW, and they are the ones which are 2n-4 dimensional, so they are lower cells. Yeah, and sure, in the planar case. For example, for n square MHV, we would have things on 5 lines. Of course, the general cells will be just in P3. They will be not restricted to 5 lines and 2 planes. Yeah. Okay, great.
Sorry. Is there an easy way to say why it's 2k plus 1 there? I mean, a geometric way, or is some other way to understand that?
You mean so there is an easy way how to see it from BCFW. Because the BCFW always merges 2 subamplitudes together. So that gives you basically, it kind of merges 2 different configurations together of these points. And that gives you on how many lines it lives. Yeah, of course, maybe there is some more kind of formal.
I mean, you can think of it as a leading singularity. And if you think of it as a leading singularity, then it's a bit clearer as to why it should have the degree it has.
Yeah, right. Okay.
Yeah. Now the general, this is only the BCFW terms. The general cells will be not have this not satisfied yet. They will be more complicated. But the BCFW ones. Yeah.
Actually, sorry. One more question. I mean, so this is given by be specified by a list of cyclic triples then, or something? Or
triples.
You had a paper a while back with Postnikov and Nima.
Yeah. I will mention it briefly. Yeah, that's non-planar. This is all planar, what I've been doing so far. This is in non-planar. There will be some cyclic triples, indeed. So here it's just this configuration. You can exactly say like which minors are 0. That's the guys which correspond to points on a line, and which minors, and the rest is positive. Everything what is non-zero is positive.
Okay, thanks.
Okay, great, thank you. Okay, so let's now look at the non-planar BCFW geometries. And the first thing is not just BCFW, but the general non-planar geometries for MHV case. So for the case of MHV or G2N, we know that the positive Grassmannian corresponds to these endpoints on a line with a given ordering, 1 to n. And we can always reorder, so get a different positive Grassmannian with a different ordering. And now if you, of course, it's kind of obvious from that geometry of points on a line, if you take all different orderings, you just get all possible configurations of endpoints on a line. So these different positive Grassmannians, G2N, completely tile the general Grassmannian G2N. Just from this picture, it is clear. Now, of course, this is not kind of nothing new because we just reorder things in this geometric setup, but we can then consider non-planar on-shell diagrams or play big graphs. And generally, these graphs will not correspond to a single ordering of endpoints on a line, because of course there is no cyclic ordering in graph like that. And yeah, indeed, in this paper with Nima, Jake, Freddy, and Alex Postnikov, we work out the positive geometries for these general MHV non-planar on-shell diagrams. And the thing that you have to do is to specify certain triplets. They correspond to the black vertices in my definition of black and white. And each triplet has all the 2x2 minors inside it, like 1, 2, 1, 3, and 2, 3. They are positive in this ordering. And that specifies you some set of these positroids, and the positive geometry corresponding then to the diagram is just the union of all these positive geometries of G plus 2 and with a given ordering. So in this case, it would correspond to seven these orderings, and then the canonical form would be just a sum of 7 Park-Taylor factors corresponding to the given ordering. Yeah. So yeah, so this is for MHV cases understood in general. Yeah. And
Well, 7 or 8, depending on how you orient things, right?
Yeah, yeah. If you orient it differently, you get a different space, but the form will be the same. So here we mainly focus on the form. Yeah, you know very well about it. Yeah. So yeah, so depending like how you orient it, you get different set of these geometries, but the form is the same because there is a relation between these Park-Taylor factors. Yeah. Okay. So now we would like to look at G36. Now, there is a very nice thing that there was a complete classification of the non-planar G36 plate big graphs or on-shell diagrams by Jake, Sebastian Franco, Conca Wen, and Daniel Gavone. And they gave us they draw all possible diagrams, then they identify which are equivalent, which are related by moves and so on. But in the end, they gave us the list of independent diagrams and the log forms. Yeah. So one thing, or the original motivation here was to figure out what is the positive geometry associated with that. Yeah. So what is the analog of the positive Grassmannian, the configuration of these points on lines, and the signs of minors and so on. But it's kind of very hard if you just look at these results to directly get it, but we will get some use from these BCFW recursion relations, and then we will also get back to the list of things and identify the terms.
Yeah, if I can just, I know you're not talking about that, but if I can just ask what the sort of challenge would be up there. So let's say even for all the top cells, so they have all sorts of top forms, right?
Yeah, I will talk about it in the end. I will talk about the top cell. We will actually identify some of the top cells. Yeah.
Oh, okay, great.
It's just that if you have the form, it's not clear what geometry you should draw. You know about the first boundaries, but you don't know where the points are. Yeah.
But if I say in the planar case, if we never knew about the words positive Grassmannian, we would still draw, from our point of view, we would draw these planar diagrams. We'd have the edge variables associated with them or whatever. but that from that point of view, the sort of the miracle is that it's possible to assign signs to these guys.
Right. So here it's not clear which signs there are. Yeah,
right.
it's
so
not clear what are the signs.
That's the question. So
That's
there's
the
a D-log
question.
form,
Yeah.
but it's not clear if there's some choice of signs.
Exactly.
Or indeed whether there's a choice of signs for both the poles that show up in the form, as well as a bunch of other ones that cut out the positive geometry associated
Exactly.
with that.
Exactly. That is the challenge. That's the challenge to assign
And
the signs.
and so these guys didn't really talk about that. They just made a list of diagrams and D-log forms. Is that right?
Yeah, because of course we have the on-shell diagrams, the things that we did can be straightforwardly done in the non-planar setup. We can construct the C matrix, we can calculate the form, but now we don't have any signs. There is no positivity, right? So that is the challenge here.
Okay.
And we will kind of indirectly start to understand it from the BCFW, because the BCFW will generate the geometry for us. But it will be not the top cells, it will be these lower dimensional cells, but we will be still able to make the connection, in the end. Okay, so we will do a different start here. We do the BCFW again, but we do non-adjacent shifts. So we don't shift n and 1, but some 1 and k. And we will calculate these terms, very straightforward, and we will identify them on the D-log form on some positive geometry, which will be related to these positive geometries of points on free lines, but it will be not ordered. There will be kind of some changes. Yeah, we will see. Okay, so let me first look at G35, and I wanted to first review again the planar case when you shift 1 and 5, so adjacent guys. This is the positive geometry that you get for G35. Of course, it's dual to G25, so it is a top cell, and it's just 5 points in a plane. But I will just organize the 5 points in this way. Of course, there is no condition on these 5 points, so you can draw it however you want. But it will be kind of useful to draw them in these 3 lines when 1 is here on the top. But again, here there is nothing special about 1 in this picture. It's just a pentagon, convex pentagon configuration. And yeah, and all the 3x3 minors are positive. Yeah, everything is convex, positive, well oriented. Yeah, and the D-log form here is this. Okay. So now let's do the same thing. So just 5 points, which is kind of very trivial, but using this non-adjacent BCFW shift. So we shift 1 and 4, and we calculate this term. That's straightforward to calculate it. And then we will see that we can identify it with a following configuration. So I will again note in the picture these special points for head now and P, because they will again play the role as these intersection points. And you see that this configuration, maybe you can here look at the button without the pollution of these 2 points, looks similar to the planar one, but the point 5 is kind of off that pentagon. Yeah, so it's this configuration. So the D-log form on this configuration reconstructs back the form for this BCFW diagram. And if you list all the minors in the planar case, everything would be positive. Here, one of them is negative, 3, 4, 5 is negative, and 2, 4, 5 doesn't have a fixed sign. So that's the geometry. Of course, you can draw it in a different way. You can draw 5 here, and that would just correspond to 5 going to -5, but that doesn't really change the geometry. So we just choose it here such that as many things as possible are positive. But again, it's equivalent geometry. So this is the positive geometry which we get from this first BCFW, non-adjacent BCFW term. And there is one more. Yeah. So in the planar case or in the adjacent shift, there was only 1, but now we have 2. And the other one, if we do the same game, actually corresponds to this positive geometry, which is now planar. Yeah. So it is now actually planar, but it has a different ordering. And you can start to see a pattern which was already there in the planar case, but wasn't that visible because of the cyclic ordering. The points 1 and 4 just show up next to each other always in this configuration and also in this configuration. Before that, when we did like the adjacent shift, the 1 and 6 always showed up next to each other, but it was because of the ordering, yeah, or 1 and 5 for 5 points. And yeah, anyway, that's the general thing. It's actually easy to understand it from this kinematical setup that once you do the 1K shift, the 1 and K always show up next to each other on a line. Okay, so this is a kind of recap of what we did so far. So the 1-5 shift, which was the planar or the adjacent shift, which generated the top cell of G3-5, and the 1-4 shift, which is the first example of this non-adjacent, generated a collection of 2 cells or 2 configurations. And together, the sum of the forms of these 2 guys recover that form. And here, in this case, actually, at the level of forms, we can always take this non-planar configuration, and we can use some U1 decoupling identity for forms. We can basically move the point 5 on this line to all different configurations, and we can write it as a sum of two convex configurations with different orderings. But this is not possible in general. So at some simple examples, you can do it, but at some more complicated examples, it doesn't help you, kind of. Yeah, just doing this U1 decoupling for forms doesn't make the non-planar configuration planar. Yeah, but here it works. Yeah, of course, here everything is very simple. Okay. Any questions here before we go farther? So we continue to 6 point, and we use kind of the shift which is closest to the adjacent. So instead of shifting 1 and 6, we shift 1 and 5. And again, it corresponds to summing some of these BCFW diagrams. And we again identify the special points, and we write a Park-Taylor factor form in this configuration. So that is the reason why kind of I introduced these special spinners, identify them, because then writing the form is very easy. Yeah, you just write really just the Park-Taylor for everything that you are allowed to merge, you write as a pole. But here you see there is some numerator factors. So that's what I was talking about. I was answering to Song. In these planar configurations, there are no numerator factors really. Yeah, there are some overall numerator factors which then go into the d mu into the measure, but they are not interesting. But this is an interesting numerator factor, and I will show just in a second. It must be there because there is some potential of generating a double pole now in the denominator. Yeah, things are not convex anymore, so you can kind of approach 0.5 head from 3 different sides, and that causes some potential problem in the denominator. Anyway, but that's the form that we get, and again, the straightforward calculation of the BCFW term just agrees with this picture of Park-Taylor factors on 3 different lines. And the positive geometry is again following. So it's kind of almost the original convex geometry, but one point is kind of off here on the other side. And we can again, if we already have this configuration of points, we can just write down the minors. Yeah, one of them is 0, the 1, 2, 3 is 0, the rest is positive. 4, 5, 6 is negative, and 2 of the minors don't have fixed sign. So that's the positive geometry here. And I will not bother you with details. We can do for all other configurations. In this adjacent case, there were 3 cells or 3 terms that we had to calculate. Here there is more, and you can all identify them as again some configuration of 6 points on 3 lines, but not necessarily convex. And here there is, then in the end, we get 7 configurations. And as I said, the 7 configurations are basically generating by having 1 and 5 next to each other on one line and kind of distributing the remaining points based on certain rules. And these rules are basically dictated by BCFW. They kind of tell you how you should distribute the other points. While in this planar, the adjacent shift, the 1 and 6 were always next to each other, that we didn't even see it, but that was just forced on us by cyclic ordering. And the rule there was redistributing all other points on the 3 lines in this cyclic ordering. So all possible distributions. Here it's similar, but it is not the same because you see 1 and 5 are next to each other. So you have to do something with the 0.6 and then the 0.2, 3, 4. So there is some sort of double cyclic ordering when you redistribute points between 1 and 5, in this case only 6, and the point between 5 and 1 from the other side on the remaining lines. Okay. So now these BCFW terms are also examples of on-shell diagrams or plate graphs. You can just follow the standard procedure. So you have two 4-point amplitudes here in the corners. They correspond to these box diagrams. But unlike usually when we do the adjacent shift, you just connect 6 and 1 using BCFW bridge. Here we just connect 5 and 1, so we get this non-planar object. And this is, for example, one of them, which was classified in this paper by Jake and Jake Trnka, Sebastian, and Daniel. And it's just one of them, one on their list. The diagram looks different because there are many like square moves and so on, but we can just compare the form, and the form is the same. Yeah. So, and other terms that we generated at 6 point also can be identified with their terms on the list up to some relabeling. Okay, so the general G3N. So this is how the expansion in terms of these positive geometries looks like. So for the adjacent, again, I am repeating that many times, we get a configuration of these positive geometries, and the amplitude was the sum of D-log forms on them. And for this non-adjacent, so that's the kind of simplest non-adjacent 1 and n-1, we get also some of these positive geometries. But now, as we can see, some of them are kind of non-convex or non-planar. Yeah. So there are it still points on 3 lines, but not necessarily convex and not in the same ordering. Okay. And for the general AB shift, so I just did this minimal shift 1 and n-1, we always get these 2 and -4 dimensional configuration in G3N, and they basically all are associated with these geometries. Yeah, so points on 3 lines, but there are points on 2 of the lines which are kind of on the other side of this intersection point. And we can easily calculate their D-log forms. The question is there any nice combinatorial description of these guys? Of course, we can just write the inequalities trivially, and the question is if there is some combinatorics. Of course, it will be more interesting for the top cell, which I will get in the end, but yeah.
Just quick, may I ask a question?
Yeah, sure.
I mean, it seems like, I wondered if you tried solving the k=3 scattering equations for this. And I mean, if you had thought about doing this, and the reason is that we had looked in the CGM paper, we had looked at a single non-planar integrand, and that corresponded to a maximal cone in the tropical Grassmannian 3.6, which is a non-planar object. I mean, it's not in the positive tropical Grassmannian. But it seemed like that maybe that would be the shaded green part could be, yeah, I mean, the non-positive tropical Grassmannian might be a place to look for that.
Yeah, like you mean for some combinatorial description. Okay.
Yeah, exactly.
Yeah, that's
so just, I mean, it's kind of an obvious thing to do, but yeah.
Right. Yeah. Okay. Okay.
But
so
it's not going to be one object. There's a whole bunch of different objects. So I think it's going to be about sort of subdividing the Grassmannian into other pieces that are not, unlike in G2N, where we can cover it just with different orderings of positive Grassmannians. We know that, of course, the full Grassmannian can be is covered already in G3N in more interesting ways. And I think the question is whether all those other pieces can naturally be associated with positive signs for minors or composites made out of minors or something Yara will tell us about now.
Yeah, so I will give some examples for that. Yeah. But yeah, so far we are just playing with these 2 and -4 dimensional cells, which of course mathematically why to do this, but there is this, yeah. Right. There is this physics connection that we care about these cells, but
well, I mean,
yeah, but
it's interesting to ask a question like about the topology of these non-planar cells, right? Like, what does it look like? How do we? Yeah.
Right. Yeah.
Are they?
So here you can
all that kind of stuff, right?
Yeah. If you look at this, you can probably think about like different ways how to combinatorically describe it. Yeah, there is one kind of permute. I think you can kind of find 2 or 3 permutations which would do it. The question is, this is just 2 and -4 dimensional cells, so you can do anything here. The question is how it generalizes to the top cell, where you really care about it. Yeah. So that's the question. Yeah, here what I'm doing from the BCFW point of view, it's very much form oriented. So yeah, But of course, these other questions are important, and I will say something about top cells in the end. So I just wanted to mention here that, again, just that these D-log forms on the planar configurations corresponds to these R invariants. For the general case, not just these 6-point examples, I can kind of use the procedure, as I said, like adding these 2 extra points, adding their lambdas, and generating the expression. Now, for the non-planar configurations, we can do exactly the same, and we again get some canonical D-log form now with this special numerator, which will cancel some double poles. And yeah, in some sorts, it's some non-planar analog of R invariant. Of course, R invariant, there is a dual conformal symmetry. It corresponds to some corresponds to the simplices, triangulating amplitude and so on. So of course, nothing like that. You have any idea about it here, but just from the point of view of a D-log form on some positive geometry, this guy is just an analog of that. Yeah, it's a very similar structure. It just has more poles and it has some numerator factors. So the question is if these, and the 3-level amplitude is a sum of these objects. Yeah, so it's some non-minimal way how to write a 3-level amplitude, not in terms of R invariants, in terms of these R primes. The question is, one can ask, is there any kind of subpart of dual conformal symmetry which survives here, for example? Yeah, so we don't have definitely the full dual conformal symmetry, but some part of it which corresponds to some partial ordering. And I can just say here, the numerator, it's kind of clear from the picture. We need the numerator to cancel the double poles, because here the point Q2 shows up 4 times. So in order to have just the D-log form, the D-log singularities, it needs to show up just 2 times. You can kind of merge 3 and Q2, Q2 and 8, and then you can remove Q2. But here it shows up 4 times. There are 4 poles, so you need a quadratic numerator to cancel a potential double pole, which would correspond to sending lambda Q2 to 0. Okay, so therefore the numerator is needed here. Okay, so now we arrive on the non-planar G36 top cells. So the physics corresponds to these 2n minus 4-dimensional configurations. Of course, mathematically, the top cells are fundamental and more interesting. For G36, these all top cells, these all on-shell diagrams corresponding to 9-dimensional top cells were classified again in this paper. So we will use it. And what we want to is to identify the positive geometries, and we have some help because the codimension 1 boundaries correspond to these 8-dimensional configurations, which is exactly this 2n minus 4. So the ones we already studied. Okay, so the simplest top cell they list there, they give this particular form and this on-shell diagram. And now we know that if we go on a boundary, we set one of the minors to 0, we get 8-dimensional cell. And this will be actually just from the form. We already calculate the form for our positive geometries from BCFW. So we can actually go here 1 by 1 on poles and just see what the form is, and if the form is the same as we got from BCFW. And in actually 7 out of 9 cases, it's exactly one of these configurations we already had. Or the form is the same. Once the form is the same, we already know what is the geometry because the BCFW generated for us. One pole gives some new geometry, but once we know the rules of the game, we can actually identify. It's kind of identifying backwards. These 6 boundaries are already enough to generalize and guess what is the top cell, and then the last one actually follows. So the 9-dimensional configuration looks like this. So I just remind you that for the positroid, it would be an hexagon. For G36, convex hexagon. Here it's basically, and this will be a more general pattern, you start with a pentagon and you put 1 point inside some triangle inside that pentagon. So, so that's the configuration. You can just write all the signs of all ijk, and everything is positive except again 2 signs are undefined and one of them is negative. It's the 3, 4, 5, which is negative here. Which is the 4 in the positroid case should be kind of here in this triangle, but it moved here to that triangle. So that is the change here. And all the boundaries, of course, corresponds to moving with these points on lines. And we recover all 8-dimensional cells from that. We can do the same. And once we kind of get the idea, we can look at other cells.
Yeah, can you go back for a second? Sorry, can you just go back for a second? I just want to see. So, so one of the guys that was negative is actually a pole of the form.
Yes.
But a bunch of other things have fixed signs that, of course, don't show up as poles of the form.
Exactly.
But get exposed as you start taking residues.
Right. So the things that are poles you can see from the geometry, like whatever you can move. Right. Yeah. So that's kind of here. Whatever you can move somewhere and doesn't hit something else, then it's a boundary. If it hits something else before, then it's not a boundary. It's as usual. Yeah, as usual. Yeah. So anyway, it's kind of surprising. Maybe so the ones I will identify will be kind of the simple ones of that form. Of course, there might be some more complicated cells, but it seems to be that there is something kind of special on starting with these, like in this case, with the pentagon and putting the last point in the middle somewhere. Mm-hmm. Yeah, and yeah, this is the same case for the what they call gamma 3, another non-planar on-shell diagram. So there is like 27 of them, if I am not mistaken, as the top cells. And here again, you start with this pentagon and you put the extra point here inside the triangle here. And again, here are the signs. Okay.
Just a thought. I mean, it might be interesting to look at the torus orbit. I mean, what are the other representatives under the? I mean, just like in the same sense.
Yeah.
What's that?
You mean other representatives of the Pleiadic graph, or?
No, I mean like. I mean, if you just other representatives in the torus orbit, like I mean, when you pass to the quotient by the torus, take the compactification, then anyway, I mean, you get a collection, an equivalence class of matroid cells, and I just thought that might be an interesting thing to try here.
Okay.
Okay. Anyway, thanks.
Yeah. So let me just So using this idea, once you know that there is something special of putting these points, you can identify 2 more cells when starting again with here quadrilateral and here with triangle and putting more points in the middle. So here it's actually multiple points in the middle and they are kind of non-interacting. Yeah. So there is so that one is really trivial, and that one, of course, you can guess what happens for any number of points. You start with triangle and you are putting everything else inside that triangle. And the form is trivial because the only poles are when you put one of these points on the boundary of the triangle, and that's basically it. Yeah. So using that, you can just guess, but I don't know if these are on-shell diagrams. I'm just guessing from what we saw here. So these guys are the potential G3 and these non-planar top cells. Okay.
Okay, sorry, go ahead.
Yeah, no, I just wanted to end here that, yeah, so we did this identification of these geometries using BCFW, wrote the D-log forms, found positive geometry for several of these top cells. Not all of them, there are just some more complicated. So these were kind of the ones which boundaries were these BCFW geometries, which were also only subsets of all geometries. Yeah. So now the thing which kind of is puzzling for me, so what is special? Because if you just look at this, you can just think about a million other geometries you can draw. But they are probably not on-shell diagrams because there is really just a limited set of these on-shell diagrams. So there is something special about these guys and not about like other guys. Yeah. So that's an open question. Why these and why not the others? Yeah, because
for
these
example,
geometries.
Can I just ask, like, if we take your picture on the left here and we just declare that 6 is inside the like top little triangle there rather than the bottom one, is that in the list or not? Do you know for a fact that there are things that you can draw that aren't in the list?
No, I don't know for a fact, but these are the only ones which don't have boundaries, which are intersection of points. Yeah, so these are the only simple ones.
Ah,
so these guys are the only ones which have like linear poles. Everything else starts to have quadratic poles.
Right.
So that kind of tells me that these are the only simple ones. The others are not simple anymore. Yeah. So therefore, probably the answer to your question is no. Yeah, because of course I can imagine many other simple geometries, and they are not on geo diagrams. Or non-planar.
They're not on geo diagrams. I guess it's possible they're not positive geometries.
Maybe there is some. Yeah, maybe they are not. Yeah. Then the question is, why? Yeah, how to understand?
Anyway, that's what you're getting at. Sorry, I didn't mean to interrupt. Sorry, go ahead.
Yeah, no, I don't have an answer to that. So that doesn't. Yeah. So now, so I think that's the big question. We also look at G4N. So I have a little bit data there, and it again corresponds to starting with the points on these 5 lines and moving them kind of on the other side, like in the non-convex positions. So that I think is a general story about. But now again, we are 2n minus 4 dimensional, so it's very far to go to the top cell at that point. Yeah. Now these guys should also triangulate the amplituhedron, the set of them, or the momentum amplituhedron, because of course there's some via BCFW recursion relation just gives you the correct form for the amplitude. So they should correspond to some triangulation. I don't know in which space it will be more visible, but yeah. And okay, something I'm really interested in, but it kind of has nothing to do with the geometry itself, is to replace the D-log form by something like gravity form and reproduce from that the free-level gravity amplitudes. But that is the question about the form, not about the geometry. The geometries are actually the same for gravity because they are just given by the kind of combinatorics of the BCFW, and that's it. Yeah. The only thing is that for the gravity, it doesn't matter how things are ordered on that line. Yeah, so there is nothing adjacent, non-adjacent. This goes away, and everything is just in a form. Yeah, the geometry is the same. Okay, that's all. Thank you.
All right, thank you. Questions?
Yeah, just sorry if I could follow up something Nima had said about the integrands. Sorry, I just wanted to bring this up before. I mean, you have these to get the dimension, a basis for the space of integrands. You have to include not just the k-part Taylor factors, but other objects. So I just wondered. I mean, you have a complete list, a basis for a 3.6, 3.7, or just wondered if like what sort of what you might know about that and what sort of generality. I guess that was just, that's it. Thanks.
No, the BCFW, you mean to these 2n minus 4 dimensional cells or the top cells? So the BCFW gives you the set of these 2n minus 4 dimensional cells that you need for the amplitude. It just generates it for you. You don't need any basis. Yeah, you just choose the shift and generates the set. Yeah, and the question about top cells is kind of different because that's a different dimensionality. Yeah, in principle, what Jake Trnka and company did for G36 was just generating all possible graphs. And yeah.
No, I mean, what I meant is for k equals 2, right? You can express any leading singularity as a just by shuffling together part Taylor factors.
Yeah, here you cannot.
You cannot, but I think my understanding is that you can enlarge the space of denominators to include compound determinants. Yeah. And you can get a basis in that set, I've heard that.
That's what Yara was referring to, that Jake et al. Classified. So that's in a sense they classified every possible leading singularity, even going all the way to the top cells that you can get, and they wrote down all these forms, and indeed some of the forms have compound determinants.
Indeed. Yeah. So
I was wondering about like a minimal basis though. So like for k equals 2, you can have just the part Taylor factors like span everything.
Yeah, you mean like a minimal set of some kinematic invariants you need. Well, you for example can see, okay, even what I did. Well, we for example know from G2n there are these inverse soft factors, so they will be there also for G3n. So some of the terms will be linear combination of just the positroid cells. Yeah,
Or,
but
yeah, or
some of
just,
them not. Yeah, but I don't know. Yeah, I don't know. That's a good question. Like, what is the minimal set?
or linear
don't-
relations in general between these things, or yeah, I mean,
Yeah,
a
there are
minimal-
these. They are kind of these. Well, at least
Like-
there are definitely these U1 decoupling-like identities when you start to move one point on all possible configurations on a line. Yeah. So, for example, here you take 5 and you put it at all possible configurations, and the sum of these forms is 0. Yeah. So there are relations like that. So that will definitely relate some of these non-planar to the planar, but at some point you are just start to cycling inside these non-planar ones, and you cannot get out. But again, these are not all G36 cells, the 8-dimensional. So there are others which don't show up in BCFW and are on shell diagrams, and they start to have these more complicated quadratic poles. Yeah. But but I agree. Like there should be some relations between them as well. Yeah, but I don't know what is the minimal set. Yeah, what is the minimal set of these guys?
Sorry, but do you have understanding of this non-planar BCFW representation equals to the original planar one, or do they tell you about the geometry? You mentioned that this non-planar one can also be a triangulation, but you don't mean like a actual. You mean some triangulation that involves like add and
in a different
subtract
space. Yeah, no, like no, not in this space, right? Not in the G36. You have to go to the amplitude-hedron space and then it triangulates. Right. Yeah, but that's very far from this, right? So yeah. So that's a good question. I haven't done it, but I guess the question is, can you just relay these two expansions using this kind of simple identities, like these moving these points around, like these U1 decoupling identities? Question: can you relate this to this? I don't know. That's a good question. Or do you need more? Yeah, because I agree. In the end, the forms here and here are the same. So can you relate it at the level of geometries? Yeah, as of course, there are these residue theorems. Eventually, they will relate them, but you have to go very, very way up in the dimensionality, maybe even to the top forms, yeah, or the top form geometries. Right. Because that's how it works with just two different representations of the BCFW, right? At 6 point, you have to go to top form. There is a GRT and relates these three to these three. Now, even if the planar case, if you want to go to higher n, and relate two different representations, it would be some sequences of GRTs. It's not so straightforward to see that one is related to the other. Of course, it's true and you can prove it, but yeah, it requires many GRTs. Yeah. So, and I guess here it's even more because there are many of these top form geometries. So yeah, I agree. It's a good question. Yeah. I'm guessing it is still some sequence of these geometric GRTs, but yeah, I don't know.
I have kind of a converse question, which is that, I mean, in the ordinary planar case, you could, of course, either begin with the on-shell diagrams / playback graphs, and then observe that if you make certain sign choices for the edge weights and so on, you make positive matrices, or do it the way you were doing with the picture to kind of see that some notion of positivity is natural. So starting with the graph, you kind of discover that there is some interesting positivity associated with it. But there's a sort of backwards direction, which is in some sense more remarkable, which is you've never heard of graphs, on-shell, playback graphs, nothing. You just ask this global question, take a k-bind matrix, make all the minors positive, and then kind of amazingly, that is associated uniquely with building graphs. In other words, you take this very global question and you realize that the answer is given by breaking it up into simple pieces of gluing together black and white vertices, and that there's a one-to-one correspondence between those things. So my question is, let's say you never heard of your non-planar graphs, but you just decided that you're going to impose these funny positivities that you can maybe motivate by drawing your nice pictures like that. So that's very nice. You draw some nice pictures. Is it somehow clear? I'm guessing you're going to say it's not clear, but anyway, it sounds like a nice question. Whether everything in the Grassmannian that satisfies these modified positivity rules is actually associated with non-planar.
Well, I can actually, well, maybe I can, yeah, of course, it's not clear, but I can maybe here go backwards. If I have these inequalities, I can draw this graph, this diagram, right? That's trivial. I can draw it. The things that satisfy these.
Yeah, you're right.
Once I have this diagram and I know about BCFW, I can say that this is a BCFW bridge of two MHV amplitudes. Once I have this diagram, I can turn it into an on-show.
Okay, I think I got it. You're saying that actually that maybe it's close to clear, because just repeating what you said, you take the picture, you draw the graph, and then you apply a sequence of sort of inverse bridges to collapse it down to the final degenerate configuration. Right. But I wonder, could it be that some of the pictures that don't seem to make an appearance, there's some obstruction to doing that?
Maybe, yeah. Well, the thing is that well, of course, it's harder to apply it on the top forms because they are not the BCFW terms. But maybe one can do this exclusion at the level of these 2n minus 4 dimensional cells.
Well, except even with the top forms, we have this notion of adjacent shifting that even if it's not BCFW. So you can't imagine drawing such a configuration and just asking whether starting from that configuration, there's a canonical way of undoing shifts to take you down to
that is true. Yeah. In
a sense, I mean, anyway, this at the planar level, this is the sort of the 0th order deep thing, the global to local connection
so maybe there is just from this point of view something wrong with putting these points at like random positions here. Maybe they have to be here together for some reason, that if you put like one point here and the other point here, there is something bad about it. I don't see it, but that seems to be the case because all these configurations are anyway.
Well, there hopefully is something bad, because independent of these examples, we know that you never get anything bigger than a single sort of cross product downstairs, right? In the G36 example. And yet, certainly from just drawing configurations, we could imagine drawing more and more complicated sort of dashed lines here that would correspond to multiple intersections and higher determinants. So
remember we had this discussion. There seems to be this infinite geometries, but from on-show diagrams we only get like finite subsets. So
so hopefully, or maybe there's some obstruction to doing the sort of shifting business in order to try and make it happen somehow.
I think that's a great question.
Okay, let's thank again, thank Jara again for this wonderful talk.